Has this ever happened to you? You're getting ready for work and you decide to brush your teeth. You turn on the water and you notice the sink is backing up. Maybe the faucet's running too fast, or maybe the drain is partially clogged. Either one can create a problem. But if the faucet's running while something's also blocking the drain, you can notice the water rising much faster. Now imagine the same thing happening across an entire city, with heavy rain coming down, rivers flooding, and storm drains not functioning. Scientists call this compound flooding, and new research out of Texas suggests it will become an increasingly important part of flood risk as the climate changes. Welcome back to the podcast. I'm Dr. Mack, and this is the Climate Translation. When we say a place is flooded, we typically mean there's too much water for a region or area to handle. But if you're a hydrologist, someone who studies how water moves on the planet, a meteorologist, or an engineer trying to understand what happened, there's another question you need to ask. Where did the water come from? That's important because not all floods work the same way. Let's start with something familiar. Heavy rain falls faster than the ground can absorb it or our drainage systems can carry it away. So the water begins collecting in streets, parking lots, yards, and low-lying areas. Scientists call this pluvial flooding. Pluvial simply means related to rainfall. And importantly, you don't need to live anywhere near a river or an ocean for it to happen. You may have seen this. A thunderstorm produces several inches of rain in a short period of time, and suddenly an intersection that was perfectly dry an hour ago is now underwater. Then we have river flooding, or what scientists call fluvial flooding. In this case, rain falling across an entire watershed eventually makes its way to streams and rivers, and those rivers rise until they overflow their banks and spread across the surrounding floodplain. This type of flooding may happen hours or days after the heaviest rain has ended, because all that water needs time to work its way downstream. Then along the coast, you have another source of water altogether, the ocean. Strong winds associated with hurricanes and other coastal storms can push seawater towards the land, creating a storm surge. High astronomical tides can raise that water even further. And today, the surge is occurring on top of sea levels that are already in many places higher than they were several decades ago. We've traditionally been pretty good about thinking about these hazards individually. How much rain can a drainage system handle? How high does this river normally rise? How far inland can a storm surge go? But nature has many paths to choose. Imagine a tropical system approaching the coast. Heavy rain begins falling inland. That water enters storm drains and streams and begins moving downhill. The rivers rise and carry more water towards the coast. Under normal conditions, much of that water eventually drains into an estuary, a bay, or an ocean. But at the same time, winds from the storm are pushing seawater towards the shore. The tide is rising. The storm surge is building. Now, water is approaching the same community from multiple directions. That's where compound flooding begins. It isn't a case of two floods happening next to each other. It's different sources of water that are influencing one another. A swollen river reaches the coast and encounters high ocean water. Its ability to drain slows. Storm drains that normally empty towards the coast encounter water pushing back from the other direction. At the same time, rain is falling. The faucet is still running, but the drain is beginning to close. That interaction causes water to accumulate in places and reach depths or remain longer than we might expect if we calculated each hazard separately. And the different pieces don't have to peak at the same moment. A river can be rising after the storm surge has peaked. Soil can be saturated when another round of rain arrives. One event can leave conditions that make the next one worse. That's what makes compound flooding so difficult to predict for and to plan for. We're not just adding one source of water on another, we're dealing with an interconnected system. And nowhere is that connection more obvious than where rivers and drainage systems finally meet, at the sea. If you want to see what compound flooding looks like in the real world, one of the best examples occurred during Hurricane Harvey in 2017. Most people probably remember Harvey because of what happened in Houston. The storm came ashore in the Texas Gulf Coast in late August. But after landfall, Harvey slowed dramatically and spent days dumping extraordinary amounts of rain across southeast Texas. Some locations received more than 50 inches of rain. Houston experienced catastrophic flooding, but about 90 miles to the east, another community was dealing with its own disaster. Port Arthur is a city of around 55,000 people near the Texas-Louisiana border, and it's surrounded by water. To the east is Sabine Lake. It's a large estuary connected to the Gulf of Mexico. The region is also crossed by rivers, bayous, canals, and extensive drainage systems that are designed to move water away from developed areas. During Harvey, that system was attacked from multiple directions. Rainfall across the city was extreme. At the same time, water levels in the coastal system were elevated. It's the exact type of interaction we just talked about. Water coming off the land had a hard time getting out. Years later, researchers at the University of Texas at Arlington reconstructed the flooding from Harvey and tried to separate those different influences. They modeled what would happen from rainfall alone, and then they looked at the effects of elevated coastal water and where the two interacted. And what they found was significant. Researchers estimated that about 19% of the flooded area around Port Arthur resulted specifically from that interaction between the different sources of water. In other words, simply calculating the rainfall flood and the coastal flood separately would not have told you what was going to happen. The interaction created additional flooding. And then researchers asked another question. What if we get a Harvey-like storm in the future after climate change has warmed up the temperatures and increased sea levels? They modeled a scenario where about 22 inches of additional sea level rise occurred, along with about 18% increases in rainfall. Under those conditions, the portion of the flooded area associated with these interactions increased from 19% in Port Arthur to a third. Now, those numbers aren't a prediction of exactly what's going to happen during the next Hurricane Harvey. They're a scenario designed to help scientists understand how a system responds when conditions change. It's what makes studies like this useful. Climate change isn't going to invent a new type of flood. We're still going to have heavy rainfall, we're still going to have storm surges, we're still going to have high tides. What's going to change, though, is the environment in which those events occur. Raise the average level of the ocean, and coastal flooding begins from a higher starting point. Increase the amount of water available during extreme rainfall, and more water has to leave the land. Put those changes together in a place like Port Arthur, and the interaction becomes increasingly important. Harvey showed us what happens when several parts of the water system are overwhelmed at once. But there's something else to consider. Much of what we've built along our coast was designed using statistics that assumed the past could tell us what to expect in the future. And as we have discussed many times in the past, as climate changes, some of those old odds are changing with it. To understand how we plan for floods, we have to talk about one of the most misunderstood phrases in weather and climate science, the 100-year flood. It sounds like a flood that happens once every 100 years, but that's not what it means. A 100-year flood is an event that historically has had about a 1% chance of occurring in any given year. You can have two 100-year floods within a few years of each other. Theoretically, you could have them in consecutive years. The number describes probability, not a schedule. But there's another assumption that's hidden in the calculation. We estimate those probabilities by looking at the past. In the historical record, how high has the water risen? How much rain has fallen? How frequently have extremes occurred? For a long time, engineers could reasonably assume that history gave us a guide to the future. But human-induced climate change has complicated the assumption. Just think about sea level. If average sea level rises, a storm no longer needs to push as much water towards the shore to reach a particular height. Imagine a basketball hoop that's slowly lowered, and now your shots are going in at a higher rate. You haven't suddenly become a better basketball player. Shots that were once missed can now go in easier. Sea level rise changes the threshold in the same way. And consider extreme rainfall. A warmer atmosphere can contain more water vapor, and that provides storms with the potential to produce heavier rainfall. So one side of the system can deliver more water, and one is working from a higher level. And now you have to calculate the probability of those things occurring at the same time. That's compound flooding, and it's challenging. Maybe an extreme rainfall event has historically been unusual. Maybe a particular coastal surge is also unusual. But what we're interested in is the joint possibility of the two overlapping and interacting. Researchers are finding that those probabilities are changing as our climate changes. Events that historically took a long time to return are becoming more frequent. But exactly how much this is changing depends on the location and how much future warming and sea level rise occurs. It creates a problem. A drainage system can be designed using rainfall statistics calculated decades ago. A bridge may have been built around the average of how high a river was supposed to rise. A coastal neighborhood may have been developed using a flood map based on records from 100 years ago. None of those calculations were necessarily wrong when they were made, but the conditions have changed. And in some places, climate change is changing the probability of reaching flood levels at a high rate. So what do we do if the odds are changing? For engineers and city planners, it's an important question. Cities are filled with systems designed to move water. Storm drains collect rainfall from streets. Culverts carry water beneath roads. Canals move it through developed areas. Pumps remove water from places where gravity can't do the job. And levees and seawalls try to keep rivers and oceans out. But they each have their limits. A storm drain can only hold so much water. A pump can move only so many gallons per minute. And a seawall protects only to a certain height. Historically, many of those limits were calculated by looking at hazards. How much rain has this drainage system handled in the past? How high should this seawall be based on historical events? How much water has this river ever carried? Compound flooding forces engineers to ask different questions. What happens when those systems have to work together? Imagine a coastal neighborhood protected by a seawall. The wall may successfully keep the storm surge from entering the community, but heavy rain is still falling behind it. Normally, storm drains would carry that water to the coast, but the water on the other side of the wall is elevated. Now, the structure protecting the neighborhood from one type of flooding is complicating getting rid of another. Engineers can respond in many ways. Some communities are installing larger pumps or redesigning their drainage systems. Others are creating areas where water can collect rather than immediately trying to get rid of all of it. Wetlands and floodplains can provide additional space for water to slow its movement through a watershed. And sometimes the answer isn't a new structure at all. It's deciding where future development makes sense as our flood risk changes. But none of these choices begin with concrete, pumps, or wetlands. It begins with better information. Engineers need better models that show rainfall, rivers, tides, storm surge, drainage systems, and sea level, and how they interact in a changing climate that is warming. This is not just a problem for neighborhoods sitting directly beside the ocean. Research has shown that compound effects can extend upstream into rivers and estuaries, including places where people may not think of themselves as living on the coast. It's probably the biggest lesson from this research. We have built so much of our flood infrastructure by separating water into buckets or categories. There's a rainfall over here and river flooding over there and coastal flooding somewhere else. The categories are useful for understanding the individual pieces, but the physics of water involves gravity, pressure, and the multiple pathways available to it. And as climate change alters the amount of water entering those pathways and the level of ocean waiting at the other end, planning for the next flood increasingly means understanding the entire system. Flooding has always been part of living with water. But as our climate changes, the amount of water coming into the system and the conditions waiting for it when it arrives are changing too. That's why research like this is important. Understanding that future means looking beyond individual floods and recognizing what happens when the water meets. I'm Dr. Mack, and this has been The Climate Translation. If you have a question about the climate that you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.